Yeah, there it is. Okay, I'm going to share my RStudio screen. All right, do you see RStudio here? You should see this.
Yes.
Okay, good. If I don't share the full, okay, so you'll see that I ran a little bit of the script already. So I uncommented some of these. So if you notice, you'll see a few differences in the R syntax this week. This was commented out, I believe, and same with this, the set working directory. I'm trying to get us used to working with these. In fact, I'm going to actually include a few tutorials on not just setting the working directory, but doing some stuff with using R as a fancy calculator, because I think people who are more familiar with computer science might be using R already, but there's a lot you can do with R that I think is intuitive. So this directory function will tell you what we have in our working directory, and you'll see here, what do we have? Well, look, it looks like we have our Wall Street data set that we want to analyze and take care of. We have our script that we're taking care of. I believe your name is a little bit different than mine. I just labeled it with the semester that we're dealing with currently. And we have what we call the ANOVA toy data set, just as an example. I like to include this whenever I ever have a working directory, just FYI. I have like a junk file, like a junk script file, because whenever I'm writing code, for instance, when I was editing and sort of working on the script this week, I would often come up with I would end up writing some code and then just sort of have it in queue, and then I would decide, well, I don't want to include it. So one thing I do is I don't like to throw things out. Typically, I'm not always a hoarder, but when it comes to writing code, maybe there's something you want to go back to. You don't want to necessarily erase all of the code that you've written. So sometimes you want to save that stuff. So I have this little file called dross, I tend to call it. This is just my idiosyncratic workflow. I work on a PC, so if you have like a working file, if you anything with a little hyphen, will tend to be first in your working directory. But this is my workflow in essence. I like to keep, often when I have more advanced projects, I'll keep my data in a separate file, my scripts in one file, and then my output in another relative path file. Nevertheless, for our purposes here, it's okay to have our script and our data in one location, but I encourage you to have some sort of archive file and then maybe a junk script file, because as you're working on your final project, for instance, I like to work on that. That's just my little soapbox that I like to, my spiel about, I think getting used to working with relative directories. We'll see that I ran this script, and we should see that I just loaded the Wall Street data set. And here we see the observations and variables. And we're going to do we're going to start with the one-way chi-square and goodness of fit tests in R. And we're going to, I should have loaded already the Mosaic package. I believe we have that already. We can double check that. Looks like I didn't actually. This is the reason I double check things. So let's get these loaded. And you can just double click these here. If you notice something, one thing you'll see is that the library function, we don't have to do just the library function. We actually have some options here. You can actually identify the library location. You'll see that I have a particular name for a version of R that I'm using, and it'll actually locate that library. That's just an optional argument that R sort of provides. If you click here, that's one way to actually get familiar with the syntax, is actually to use the GUI, the graphical user interface, and then you'll see it in the console, sort of populate the commands. Anyway, we load the data. The first few questions are ones that we know quite familiar, what we're quite used to, is we can ask ourselves, well, what's the sample size? In other words, what are the number of rows of our data set? What are the number of columns that are in our data set? Those are quite easy. If you notice, I've identified, if you use the load command and it's an R data file, then you already have R already reads in the data frame as what is called a local object. It's in your local, it's in your global environment, but it's in your working directory. And that's pretty familiar. What I want to promote, I would say, if you look at the syntax this week, is you'll see more of this idea of nesting functions. So not only do we have particular arguments, but we have nested arguments here. And I'm putting these on different lines, these arguments, but you'll see that we have the familiar tally function, because the first question we're getting used to or addressing is using the variable social class, what is the proportion of people in the sample? What proportion of people in the sample are members of the lower social class? Round your final answer to 2 decimal places. Here we're doing the tally function, but we're going to actually, while we do that, we're going to round our final answer. And we'll see that we come up with this answer. What we've been promoting before is the non-nested tally function, right? So let's get rid of this round command. I just saved that file. I just saved the syntax, by the way. And you'll see that there's many more decimal places. I find it's more intuitive to read. I'm going to give you a little bit of a tip here, since those of you attending might be interested in this. There's this options argument that you can also make. And you can specify the number of digits that you have. I think these are the number of decimal places, if I recall. And this actually doesn't change the precision of your analysis, but it does change the outputs. That's another way to do the same kind of stuff. The only difference is if you set your options in your console to a number of digits. The only downside is that by printing those digits, you might get an idea that you're actually already rounding those numbers, and you actually aren't. So R reads to 16 decimal places. R reads to 16 decimal places. And that's regardless of whether you specify 7 digits, or I think 3 or 2. I say 7 because that's the default. If you count here, I believe you'll see that that's the case here. 1, 2, 3, 4, 5, 6, 7. Yeah. That's actually to a precision of 16. So when it's ever estimating, say, intermediate arguments or expressions like the standard error, it'll read those numbers and carry those digits to the 16th decimal place. That's just something, it's a little bit of trivia, I suppose, but you can use this options argument to change the way you print out the analysis. So, and keep in mind that the default is to 7. I like to round as we go, though, and that's different because what that's saying is you're actually evaluating the analysis differently. Okay, so we're going to have a little hypothetical example. You've been hired to examine the distribution of people's self-identified social class is the prompt. I'm putting this on different lines because you'll see that it's a little bit hard to read if we don't have it on different lines. And the question is the prompt is, a government agency thinks the proportion of people in the population who identifies lower, middle, and upper is 15, 60, and 25 respectively. So here we have a test of a difference in proportions where we specify these differences a priori. So the first thing we're going to do is we're going to use this base R function, which is to concatenate these values. These are just, R reads these in as string functions. So you can read this in and you're just concatenating these particular values right here. And you can see this right here. If you click on this, you'll see that this is actually a vector. I'm using a little bit of slang here, but you'll see that if you even highlight your cursor over this little vector, you'll see that it's read in as a numeric vector, which simply means that there are 3 values. And you can see this in this little brackets argument here, or this brackets indicator. And that these are read in as numeric values. If you're familiar with computer programming at all, you'll see that these are actually read in as, these are different than integers. You can also read these as integers, which are whole numbers and don't really have any substantive consequence, except for the fact that if you read a numeric, say, string, if this were 1, 2, and 3, then you would use a little bit less space because there's a little bit less data used up. These are read in as, I think, double digits or something like that. I'm not sure. Regardless, it's pretty inconsequential. Just keep in mind that there is this function called the concatenate function. All it does is concatenate just simply bundles any kind of elements we have together. They can be words, they can be numbers as well. And that's the C function. If you want to know more about it, you just simply put the question mark in front of that, and you'll see this. Yeah, they even define it as a generic function. It's one of the more essential functions that you might see in R. Just be familiar with that. Now, what you can do here is you can use the assignment operator. We've talked about this before, right? So we're using the assignment operator to define what the government thinks the proportions are for social class. Then we're using the assignment operator to define the number of rows in our data set. And then we're going to define the number of counts. So assuming the distribution is true in the population, what is the expected number of people in the sample? Well, that's simply the proportion multiplied by the number of cases in the sample. And that's what we're doing in this answer to this question right here. We're essentially defining a few objects here that are useful to our purposes. So if you notice, the first object I've defined on line 61 is the proportion defined by the government using the concatenation argument. The second one is simply is actually a string function. You'll see that this is read in as an integer. That's what that L means actually. And that's just the number 800. And then we're going to give our answer, which is going to be the proportions multiplied by the sample size. And what R will do is, rather than have us calculate, and this is getting us closer to using R as a fancy calculator, we're actually multiplying our sample size by each of these proportions here. And what R is going to give us back in this last object on line 63, it's going to give us back not just one evaluation, it's going to give us an evaluation with 3 items in it, which will be the expected numbers. We see that right here. What I've done actually in my workflow, you'll see in my workspace, you'll see the last evaluation that I have. You'll typically see that here. That's not really relevant for your work. You probably won't see that. But the point is, now we have a numeric value, a vector, that we have evaluated that is simply 0.15 times 810. And we can do that for each one of these numbers individually. But the nice thing is, we're essentially doing this for each value. And this is an example of how R permits you to define objects in your workspace and then evaluate those multiply. So what we've done is we've simply multiplied this vector on line 61 times the line 62, and we've defined a new vector, which is simply just a list, you could say, of items. That's all a vector is. A vector is a list of items. And this new one is the answer that we have to this question. I'm going to go through more of this in a tutorial that focuses on some of these questions. And you'll see that these are actually evaluated to 2 decimal places, probably because I'm probably using this is probably an artifact of the options function. If you notice that the answer, if I use the print option, you'll see that it rounds to not to a whole integer, but to actually partial decimal places. It's probably because of this options argument I set before. All right, are there any questions about this? I'm going to go through the next few examples going through this as well.
No.
Okay, all right, thanks. So the next argument we're going to have is to remove some of these objects. So we printed our answer. Let me go through options again. I want to make sure digits equals 7. Let's make sure we get this all right. And then rerun the script, by the way. And I want to emphasize, if you redefine some of these objects, you'll simply see that it overrides the previous one. So I can rerun this line right here, line 63, and I can define what the government will say. So if I want to revise what the government believes to be the true proportions of social class, I can just redefine that code over and over and over again. But just keep in mind, this is one issue with R. If you want to define a new vector, say this is the number of columns, then you have to do say you have to define a new object. Otherwise, if I do define n as the number of columns, it'll simply override what I've printed already. You see, so you'll see that the number of columns is now, or the number n is now identified as the number of columns rather than the number of rows.
Yeah.
Yes, and that's just something to be aware of. So let's we could define that as, say, a different object, and we can redefine the number of rows as n. Okay, so that's something to be aware of. All right. Now, if we want to go to the actual counts, we simply round, and we use this format, and we use the count option with the tally function. And we specify, this is pretty familiar, but again, I'm introducing something a little more complex. I'm introducing this rounding function. So we're going to round our answer to 2 decimal places. It doesn't really matter because these are counts. But you'll see that the answer that we have, the actual numbers are around 156, 471, and 183. And that's simply the tally function, as opposed to multiplying the proportions that the government has and then creating a vector or a list of items. That is the number of counts that we would expect based on what the government believes. And you'll see that these numbers are different, right? What the government believes, and I print this, or I could just actually type out gov expect a number. Now, what I don't like is that this is back to 2 decimal places, or sorry, to 1 decimal place. And it wasn't like that in rehearsal. I'm not sure why. We round that answer. Let's round it to 0. We'll round it to the nearest integer. That's a little bit better. If we define what the government would say, those are the numbers for lower, middle, and upper. And then if we define ours, we'll see that number is quite different. Okay, why are these relevant? Well, basically to introduce to you this idea of the chi-square test, a goodness of chi-square function, that when we use this chi-square test, what we're trying to evaluate is whether or not these differences in these numbers across these, say, in our sample, whether or not that's different from what the government believes. And I'm going to skip over this line 83 in terms of stating our hypotheses and emphasize really this idea that our p-value, our chi-square test statistic, is an assessment as to whether or not our proportions are different than what the government would say. That's the intuition. And the syntax I introduced to you is, again, this idea of probabilities. So the null hypothesis would be these probabilities. Here I'm using this vector argument to define the probabilities. In fact, what I'm going to do before we get to that is I'm going to remove some of our other objects. If you can just evaluate this line, but it's important to keep in mind that what we have here is, sure, no problem. No, thank you, Suzanne, no problem. So what I want to emphasize here is that when we use the remove list function, we're actually removing some of these objects from our working space. And when we do the tally function, when we use the chi-square test, what we're doing before we get to that point is we're actually defining our probabilities as an object. We're creating a table which is based on our data defined by social class. So we're actually creating two vectors. One includes the numbers in our sample. One includes the probabilities that we expect based on our null hypothesis. And then our results are using this chi-square test function. And here we define our first object that we're going to evaluate as the table itself. So we're going to do a chi-square test based on these data table, and we're going to specify correct being false. These are just optional arguments, but I'm not optional, but actually important arguments. And then the P are the probabilities that we're going to assign. And the P right here is simply to assign. What we're doing is we're saying we're going to say that our a priori hypotheses, our null hypotheses, are defined by these probabilities here. And our data are defined by this table right here. And you have to specify this third argument simply to override some of the defaults. And we're going to find that as an object. And what we have here is we actually have our chi-square test right here. And that's what x squared, by the way, means, just FYI. And this, so here's the test statistic. Here are the degrees of freedom, and here's our p-value. Now our p-value is far less than 0.05. So what that means is that we reject the null hypothesis in terms of the hypothesis. We reject the null hypothesis here, essentially asserting that the distribution in the population is what we would assume them to be based on our on these percentiles here, or sorry, these proportions here. So what that means is that we reject our null hypothesis given our p-value and our chi-square test statistic, that the proportions for social class in the population are 15, 60, and 25 for lower, middle, and upper class, respectively. And you can see that the key for the output here is quite clear. And you'll see that here's the observed, here's the expected n, and we already know that because I've shown you how to calculate this. I've shown you how to calculate the observed n. And the chi-square test simply evaluates the degree to which our observed ends match our expected ends. And what this suggests is that we can reject this hypothesis that the population distribution of probabilities is this vector here. They could be something else, but they certainly aren't 15, 60, and 25 based on our analysis that we're coming up with different ends. All right, so since we rejected that, there are other analyses to do, but I want to move us to something a little more advanced, which is to extract these test statistic results. This is another good example of the object analysis, object-oriented programming that you can use. If you want to know what the test statistic is, you can simply define that as a new object. You can even round that and print that. Here's our chi-square test. This idea that is simply that with every kind of analysis that you produce, you actually can extract those results. You can manipulate those further. That's really the intuition that I want to give here. You can also do that with the degrees of freedom that are rounded to 2 decimal places. You know, that's pretty simple, I think. So what's useful when we also interpret this is to visualize our data. And here we're gonna, I'm gonna show you how to plot the chi-square distribution. I'm not sure what that argument is. It's the error saving file. I'm not sure what that meant. Okay. So if you want to do this, you can actually extract the chi-square test statistic. I'm going to show you this pdist argument again. What I'm doing here is simply taking the chi-square test distribution, and we come up with a value that basically gives us an idea of the probability of achieving our distribution based on our hypothesis. And it gives us a sort of a visualization of that p-value. Looks like it's my screen sharing function is a little bit wonky. Okay. All right. So here you can see the rounded p-value of 0.002. I believe that was in the problem set. This gives us an idea of really how well we can reject the null hypothesis here. I want to point you toward the fact that there's a p-value of 0.002. There's also a chi-square test statistic that is on the x-axis, and that's 12.14. And that's why, you know, when an earlier question was raised about, well, should we look at p-values or test statistics? Is there a different way to look at things? Not really. A p-value is a test statistic. It's just a different way of interpreting it. And this distribution, this pdist function, is a way of mapping our results from that chi-square function onto the plot pane here of RStudio. And that simply is not important. You can live your life without ever using the pdist function, I believe. but it gives you an idea of the p-value, the significance in terms of statistical significance. And here, this clearly says to us, we can reject that hypothesis of those expected proportions really being the ones that are in the population based on our sample. Okay. All right. Now, if you have a different hypothesis, let's go back to our syntax. Let's say we have a different hypothesis. We really think that we reevaluate our hypothesis. I'm going to click this little broom to clear the history. I like to do that as I work along. People have different workflows. It's something that I like to do. The point here, though, I actually like to remove some of these objects. And here we use a remove function. I think this will remove most of what we've printed out so far. It might complain. No, it doesn't seem to. Sometimes it will complain if you haven't defined some of these objects. But now we think our expected proportions are 20%, 60%, and 20%. Well, here we can redefine our objects. And here again, we're multiplying and printing out our analyses. And here we have different ends. I did what I did earlier. I basically define an object of proportions. I define an object that is the n, an atomic vector, you could say, to use different jargon. It's just simply one value, a scalar, a number that is 810. And then I define a third object that is the expected number of counts. I can print this, expected counts, and that's what we'd expect the counts to be if we had a proportion of 20, 60, and 20, and we can test that hypothesis. But before we do that, let's go back to our actual counts. We can see that our actual counts are quite different, but somewhat similar to this. I'm going to remove some of these. And what I'm going to do is I'm going to define again these probabilities to be these values. We're going to create an object that is the table, and then I'm going to use this chi-square test. And you'll see that it's the same argument as earlier. And here we fail to reject the null hypothesis. So what that suggests is that we cannot rule out the probability that's, I want to make sure we fail. Yeah, we do fail to reject the null hypothesis. So here we see the p-value. So we fail to reject the null hypothesis that the actual population proportions are 20, 60, and 20. And that makes sense because if you look at these values, they're not that far off from what we observe in our sample. And here's another way of rounding. You can define one object, as I do on line 142, and then you print that rounded object. And that gives us our chi-square test statistic. If you notice, I'm using this $$ operator. That's simply taking this object called results that we've defined on line 140, and I'm extracting something labeled statistic. That's actually defined. If you go to the help file and dig deep, you can actually see that the results object, whenever you use the chi-square function, it already prints out it actually prints out some results that you can extract that have particular labels. So you can treat it like a data set. I'll talk more about this $ operator, but that simply is a way of saying using this object or data set results that we define on line 142, and you can actually see as I highlight the word results, it actually, RStudio will highlight line 140 as well. I'm extracting something that the chi-square test function defines it as statistic and rounding that to 2 decimal places. And what does that word statistic mean in the output? Well, quite clearly, you'll see that statistic refers to the chi-square test statistic. That's just something that you would have to know if you read the help file in detail. Okay, so let's plot this value, and we are going to use the PDIS function. And this will show, probably not surprisingly, that what we already know. It's really adding no new information, but it does give us an intuitive interpretation of the results that I just described. So we fail to reject the null hypothesis that the true population distribution of social class is 20, 60, and 20% respectively. And here we see the rounded proportions that really clearly indicate that, in contrast to our previous hypothesis, which had a chi-square test statistic all the way here at 12, when we move that chi-square test statistic to a lower value, with this particular sample at least, you'll see that the p-value actually concomitantly increases. And when the p-value increases above 0.05, we will fail to reject the null hypothesis and say that, well, it seems to make sense that we have a 20, 60, 20 split in a social class, but it could also be 21, 59, and 20 as well. We're not really sure. Our values are consistent with a range of plausible values within the population. But it's consistent with some more than it is consistent with others. Let me tell you what this 0.18 means actually. What it means actually is that in similar tests, 1 out of 5 times you could actually see a value this extreme or more extreme given the sample. So technically, we can't ever rule out the possibility that we fail to reject the null hypothesis, or we do reject the null hypothesis. Nevertheless, it gives us an idea of the probability of that, rejecting the null hypothesis, failing to reject the null hypothesis when in fact the null hypothesis is true, and that's a type 2 error, as opposed to a type 1 error, which is rejecting a null hypothesis when in fact the null hypothesis is false. Let me think. Yeah, the type 1 error. A type 1 error is when you reject the null hypothesis when in fact the null hypothesis is true. Here we fail to reject the null hypothesis, and if we fail to reject the null hypothesis while the null hypothesis is true, that's a type 2 error. Typically, people look for or are on the hunt for statistical significance. So if there's an error that we tend to make, it's typically a type 1 error. It's a failure to accept the null. It's a false alarm. That's more common, a type 1 error, rather than a type 2 error. I want to take us back to this remove function. If we type remove, I want to say, as a sort of a little, as an aside, without this list, again, if you notice, I'm using the nesting of arguments here. This is something you'll see within R. I've concatenated up what I call the list. This is just the list argument within the remove function. These words, what are these words? Well, these are the names of the objects I've just defined. You typically have to do this by hand, and you notice I'm concatenating these. So I could actually define these as separately on a separate line, but I like to include them in the same argument. And if we type remove without typing any sort of argument, you're going to remove everything in your workspace. You don't want to do that. We want to keep some things, because if we type remove without any kind of qualification, then you're actually going to remove this data set here, or the data frame. And we want to keep that. I typically like to keep that working directory, character, vector, or character, we call it a vector, I suppose. It's a vector of 1, this is 1 item, but I like to keep that because that reminds me where I'm working. And I like to keep my data frame because we're going to continue to do that. So we want to just remove a few things and define what we're going to remove. I'm also going to remove this thing called C. Equals, sorry, I'm typing this in the console. So now this is what you'll see if you run the script up until line 159 or so. You should see this graph, probably see more because I removed the previous one. You'll see this working directory, and you'll see the Wall Street data frame. Now here's a chi-square test for independence. This is a little bit more common to see. The question here we're asking is, what is the proportion of those who think Wall Street executives are dishonest? This is kind of an interesting, apropos question, I guess, given the current president-elect, who is the sort of Trump you would consider to be the quintessential Wall Street executive. He's the epitome of Wall Street, you could say. Well, what's the attitude toward this profession? Well, do we think these people are dishonest or honest? What does the public opinion say? Well, you can see by social class that people in the upper social classes tend to think, are less likely to think that Wall Street executives are dishonest. If you go to a lower class position and ask them what they think of Wall Street executives, they're more likely to say that Wall Street executives are dishonest. What we do in the analysis for the problem set is we do want to ask some questions. Well, is this different? Does this vary by social class? I'm going to skip some of this other syntax, I think, for simply just to expedite. Oh, let's do this, I guess. We can go through this. That's fine. Let's see. We've gone through this. So what this says is this gives us a proportion of the population that thinks that Wall Street executives are dishonest, contingent on social class. And we're giving the proportions that we round to 2 decimal places. And now we're going to round by giving the joint distribution of each. So here we see the proportion of those who are both believe Wall Street executives are dishonest and believe Wall Street and are in this upper social class. The main point to keep in mind is when you use this plus operator rather than the vertical bar, you're no longer defining just the columns as adding to 1. Instead, you're defining the entire probability space. Each of these little rows and columns, each cell adds up to 1. If that makes sense. So it's the joint probability rather than the conditional probability that we're defining. The point here is, if you just run through the syntax, you can see that I don't want to go through this too much because I don't think this is as useful. But what this suggests, if we run through this code, is we can come up with a probability of being in the lower class and the probability of viewing Wall Street executives as dishonest. And we can identify the fact that the probability of 1, the probability that we've identified of being in lower, of D and L, that is of viewing executives as dishonest and being in the lower class is 0.14. And multiplying the probabilities we find to be a little bit different. The probability of 1 times another is 0.13. What that suggests is that those two probabilities are different. Given that the probabilities are different, it means that they're not identical, and we can identify this that 2 objects are not identical using this identical function actually. Oh, we didn't define all of the objects, so let me make sure I got the probability of 1 times the other. Probability of DXL is not identified. Oh, I know why. This is actually misprinted. This should be this. And you'll see that this is false. So actually I have to fix this. This is a note to myself. This is actually isn't that important, but it's relatively important when we go through the syntax. If you look at 198, is the first object. All we're asking here is simply, now it's complaining again, because I redefined the object. What the identical function does is it simply says, is this object the same, identical to this one? Identical in so many ways, in not just the value, but whether or not it's actually a numeric or an integer type object and the length of the object. So you can do this with data sets. If you think you have a different data set, like the Wall Street data set, let's say you make a copy of it and you want to see if it's identical to the other, you can see whether or not that's true or not. What this says is that the probability of being of your attitude and the probability of being in the lower social class is different than the probability of 1 times the other. And that suggests that the probabilities are probably not independent. That's actually the answer to the question, if we allude to that in the problem set. I'm not sure if we include all of these details here. But that's the intuition here, is that it's a way of, this is a way of identifying whether or not the sample social class varies by your attitude. Now, there's an easier way to do this, and it's far easier, which is to use this chi-square test statistic. So let's take a look at this argument. What is the test statistic? Well, we see that it's the p-value is here. We see the degrees of freedom are here. We see the chi-square test is here. So this suggests that the social class is in fact not independent from our attitudes toward Wall Street executives. It suggests, in other words, that our intuition was probably pretty correct when we just look at those, when we eyeball the distributions. There's something to say about social class predicting your attitudes toward Wall Street executives. And all the chi-square test does, and I want to emphasize this, it assesses whether or not those probabilities are the same or not. It doesn't say whether or not those increase or decrease by social class. But we can actually make a more substantive, this goes to the difference, I think, between substantive interpretation and substantive significance and statistical significance. This p-value simply says, is social class independent? Does social class predict at all the probability of evaluating Wall Street executives differently? And we find that it does. And substantively, we can go back to our simple tally argument and simply look at that distribution. And that goes to substantive significance. It's probably more substantively interesting to say, as I provide here, and on going back to line 173 here, your line will be a little bit different probably because I pressed enter and carriage return a few times and changed the lines. But you'll see that substantively, we can make a pretty interesting argument. It's pretty interesting to say that lower class, 74% of people in the lower social class will assess Wall Street executives to be dishonest, as opposed to 55% of higher class people. So furthermore, we can also say that our test statistic says that this is not just simply due to a roll of the dice, that this is not random, that the proportions that we observe in our sample are not independent from social class. So dishonesty is associated with social class. And we can go back to the tally function to give us a better idea of the substantive interpretation, not just the proportions, but keep in mind also of the count in our sample. Because if we ever give proportions, that's okay, but it's also useful to give the counts within our sample, simply because proportions don't really give us an idea of the relative numbers. And that's particularly important, say, if we have the sample, like with the Titanic data set, we have the full number of passengers. Let's see, if we go to this test statistic, yeah, the other thing we want to do is we want to plot this. So we can do this with a pdist function. I can show you the syntax here. We're defining actually something else with a concatenation argument, but what this clearly shows that our value is highly significant statistically. And that's not surprising given our results that we've evaluated earlier. Right, if we define our results here, we'll see that our chi-square test is quite high. Now, if you notice, it's almost such a high test statistic, it's not even really that informative to really look at. This p-value is essentially evaluated to 0. It's effectively 0. And you'll see that that's because those numbers are so low that it's basically a probability of 1 that our test statistic would be lower. So that low p-value, as indicated by this graph, indicates high statistical significance, but not necessarily substantive significance. So what do we conclude at the 0.05 level? Well, we actually reject the null hypothesis here. What I want to show here, though, is I keep using probably more advanced functions here, but we can actually, if you want to do something quite simple, you can just look at this output here and keep in mind that if we have this as the output, we don't have to define intermediate objects. We can simply cut and paste some of these values here. What I don't like to do with that is the mere fact that, so here we define Q, our quantile, we could say, as the test statistic. Is we can actually just cut and paste this output here. And you'll notice that the p-dist function is a little bit different. What I've done here is, yeah, so you'll see a little bit of changing of that line due to rounding, because here I've specified the value to 3 decimal places. When I'm printing out the actual object without doing any of that rounding, I'm presenting the results to a more exacting level. Substantively, I mean, intuitively, it doesn't really matter. It's still highly statistically significant. You'll see this additional argument, again, using this nearly ubiquitous concatenation argument, right? Here I'm combining 2 values. All I'm doing here is I'm defining my x-axis by the origin, or 0 point, and the value 20 here. Why are we doing this? Merely to include our value, our test statistic indicator on the graph. So that's just another argument here. We also do this with, I believe, the other argument would be y-lim. We don't really want to change that, but you could actually include that. If you want to include, yeah, see, so the nice thing about RStudio, as you'll see, is it'll give you suggestions. So if we want to define that as 0 to 1, which is how you probably want to define it, you can actually see that as, yeah, you'll see that as now I've redefined the y-axis from 0 to 1. That's probably a little more intuitive if you want. It'll include a lot of white space here. Let's remove these objects. So this is what I wanted to show to you earlier. If I'm creating a bunch of objects and I remove some of them, you'll see that with the remove function, if I don't define some, RStudio will actually complain. It'll say, well, look, I tried to remove this object. I couldn't find some of these, right? This object test stat R was not found. That's precisely because I didn't run all of the code. It's not a big deal, just something to be mindful of. So we did a one-way test of significance. Let's do a two-way. Now, this is going to be pretty much the same story, except we're using, basically, we're going to apply the independence of both. Well, here, so we're going to look at a different variable. And this is viewing the view that Wall Street executives are intelligent. And the difference here is the table results we're defining as our output that we're going to test. We're looking at the joint probability of an independence between intelligence and social class, rather than what we looked at before, which was we defined table as, no, we did the same thing here. So, no, sorry. This is the same thing. What we're going to do is we're just going to provide this with a little bit less output. Sorry, what we did earlier was a two-way test. We're still doing a two-way test of significance. What we're saying is does social class predict whether or not people view Wall Street executives as intelligent? And here you see the results are printed out in roughly the same way. Here I'm going to create the rounded objects here that are just simply the same arguments you provide in the results, except they're rounded. And you see that with a .r assignment label for each of these objects. You can even combine these using the concatenation function if you want. You have the chi-squared, you have the degrees of freedom, you have the p-value. And you see that the p-value at 2 decimal places here is 0 as well. So what does that tell us? Well, it suggests that there is some sort of association between social class and attitudes toward honesty or dishonesty in the sample. Okay, and we can also plot that as well. Again, we're going to see that with a highly significant two-way test of significance, again, we're going to see that there's a low p-value and a high chi-squared test statistic. Okay. I think the last one we're going to look at is whether or not people view Wall Street executives as community-minded. And here we see another, actually, if we tally this as well, we'll see that actually this doesn't appear to be different by social class. So here we fail to reject the null hypothesis. I don't believe this is actually in the homework. I think this goes a little bit beyond the homework, but it's an example of interpreting and actually displaying the results when they're not statistically significant, when they fail to achieve statistical significance. Let's see what that looks like. So what you see here is, because of the output, I've defined, and this is actually probably a small edit I should include. It's not really that consequential, but if you look at this code, like here I define the x-axis according to values that probably don't make as much sense. We probably want to define our x-axis by from 0 to 10, simply because we're actually cutting into this value a little bit. But what I want to show is that when we fail to reject the null, see that just simply looks a little bit better. This is where statistics becomes a little subjective. I think one rule of thumb when you talk about the adjusting the x and y axis is that you want to give us a good sense of relative degree, and you also typically want to include the 0 point or the origin of any kind of scale. If you can, and you have the space, I'd include the full scale. You know, if like the density, I'd probably include the y-axis from 0 to 1. That's not a big deal. But the main point here is that when you look at the test of a two-way, when you calculate a two-way chi-square test of significance on a two-way contingency table that is non-significant, you'll see that in terms of the p-value, this is what it looks like. And you'll see that the p-value is going to have the blue space here, or whatever color that you would have given your default graphics scheme. You'll see that the p-value is a little bit higher, and that the concomitant, going along with that, you'll see a test statistic that's a little bit lower. So here we fail to reject the null hypothesis that that the social class is independent from that is not independent from attitudes toward executives as being community minded. Probably to put it in more common terms, knowing what social class somebody is in doesn't really give us much information about whether or not that person views Wall Street executives as community minded. Now, lower people in lower social classes do view executives as more dishonest, but we don't really have, and we show that evidence to be statistically significant, but we really don't have enough evidence in our sample to claim that people of lower social classes think that Wall Street executives are less community minded if they're in a lower social class. In fact, if we look at the tally function and we look at the substantive proportion, I believe it's relatively low across all social classes, but let's take a look. That's the N. We want proportions. Proportion. Forgot if there's an S there. No, it's okay there. There's no S on proportion. Yeah. This is the point here. The idea that a Wall Street executive is community minded is pretty much low across all social classes. Nobody really thinks that Wall Street executives are community minded, but honesty and dishonesty does vary by social class. So here we fail to reject the null hypothesis. And we see in our sample, yeah, there isn't really much substantive difference. Now, this is where statistical significance is relatively important. It's possible, for example, that maybe being in the lower social classes is predictive, but not maybe once you go beyond the lower social class, being in the middle and upper classes matter, because there's a small percentage difference, 26 versus 20 versus 22. But we find that based on our p-value, based on our chi-square test of independence, we fail to reject the null hypothesis that there's no difference between social class and community-minded. In other words, that social class is independent from being community-minded. So this is where we really see most of our analyses in our everyday applications of the chi-square test, is testing these two-way contingency tables, not just simply interpreting the substantive probability, but asking ourselves, does this difference in proportions that we observe by one category, in this case social class, vary systematically by another beyond chance. In other words, as I have said before a couple of times, beyond a roll of the dice, it is simply chance that these differences occur. And it appears to be the case in our sample that, yeah, in our sample, it looks kind of like that being in the lower social class, you're more likely to view Wall Street executives as community-minded. But that's just a roll of the dice that appears to really have no consequences. Really probably not true in our population. If we could sample every American, we probably wouldn't find any difference by social class and their attitudes toward Wall Street, their belief that Wall Street executives are community-minded. It's probably pretty much equal. Now, that being said, no hypothesis would say everything is identical, but we're kind of saying, yeah, basically in expectation. When I say in expectation, I'm sort of qualifying myself. I'm saying if we were to sample enough people, odds are we're not going to really see much difference by social class. And social class is not going to tell us much about their attitudes toward Wall Street executives being community-minded. Precisely because the story here is nobody thinks Wall Street executives are community-minded, and it's probably about 1/5 of Americans, maybe a quarter of Americans, will believe that Wall Street executives are community-minded. So that's an example of really failing to reject the null, as opposed to, if we go earlier, oh, I removed that. Oh yeah, here we go. As opposed to rejecting the null. Here we can reject the null. Here we fail to reject the null. And you'll see a few more examples, I think, with the tally function with probability, but with other variables, with whether or not Wall Street executives are viewed as greedy, and other examples. I didn't get to analysis of variance. I'm going to do a tutorial on that, precisely because not everyone is interested in that. There is actually a debate in stats as to, well, do we do an analysis of variance when we could actually do a regression, for example? Why don't we just run regression, simple linear regression? There's a debate about that, but analysis of variance is still fundamental to our understanding of differences and means. The intuition, though, is basically similar to this chi-square test statistic of differences in proportions. Only we're looking at continuous outcomes as opposed to percentiles. So think of it, the ANOVA, as sort of analogous to this, in terms of interpretation, in terms of a lot of the format and application. I know a lot of people are interested in using ANOVA for their final project. I think there's even an AOV argument, but I just want to point out that here the argument is, you define it. You use the AOV argument. I think with the Mosaic package, you define the outcome quite differently. But I want to talk about that a little bit for another time. I think that's it for now. Let me see. Are there any questions at all?